May I use the restroom?
Yeah. I had this all set up for chemistry, and then I was putting it all away, and I realized, wait a minute, I need it again. Yes. Actually, I'm gonna run to the ladies' room myself, so I'm gonna leave this here.
I like your mug, James.
Thanks. I like twisted it when I went to sleep, and then it stayed.
Because I saw the duck and
The Muppets?
No, the Muppets?
The Muppets?
I grew up outside, okay?
The Muppets? Does that look like Kermit the Frog too?
He's in the puppet. It's like the same thing. She's not wrong. They literally look the same, okay?
I think
Disappointing.
I don't know if the Muppets versus Sesame Street. I honestly don't know who would I pick.
Sesame Street.
I've only seen
Big
Muppets,
Bird,
I
you
haven't
take
seen
out the
Sesame
talent.
It's outside tonight. I haven't seen
Back.
I had him as my profile picture for
You
like
gave Big Bird a 10.
one movie of Muppets and that's it.
why is he that ever done?
This thing is rubber ducks.
I don't see her. Okay, left and right. All righty. You can be turning in all your stuff unless you have a question over any of it. Huh? That's true, because yesterday was Wednesday. But I'll still answer questions. In fact, Candace has one, so I'm going to do hers on the board. I'll ought to wait till she gets here, though. All right. Okay. I want you to give 3 examples on your whiteboard. Marker. And try to give a variety when I say 3 examples, make them, different from each other. If you can. A whole number. Integer. Yeah. A rational number. An irrational number. And E, finally, a complex number. Yeah, see if I can participate yet. There she is. Hello. We are seeing if we can come up with 3 examples. Let me get this to stop moving. It's still moving. Is that 2 or no? I want 3 examples of each one. 3 examples of each one. Because we're going to be using these terms a lot, and I gotta be convinced that y'all even know what we're talking about. Is that one number?
That's one.
Oh, and then there's another. Oh, okay. I thought the comma was separating 2 numbers. I'm like, that's a number? Let's see. Okay. You going across that way?
Yeah.
Integer. This is the integers?
Wait.
So you know these weird numbers better than you know these others?
Yeah.
Oh, you went all orderly, didn't you? This one, I don't know, you might. And you're just actively ignoring your favorite fractions.
Oh.
Yeah. Oh, I like your group. Yeah, I like yours. Yeah. Okay, this is not, well, irrational. I don't think it's irrational. It's just considered down here.
Oh.
Actually, both of those. So, but you're on the right track. And this one, I think if we switch those, and get rid of that one. Okay, well, let me. Okay. Tell you what, I'm gonna go around. Let's see. Whole number 25259. Right? You like all those? Okay, is that a coordinate in space?
No.
It actually is. Okay. And integer 1785 1/2. 1/2 is not an integer. It is a rational number. Okay. 59 is rational. Square root of 49 is not rational. It's irrational. Well, actually, no, you're right. It's 7, so it is rational, and it's also an integer. You did a lot of integers in one rational. Okay. Let's try some of Miley's.
No,
No. Oh, come on. I bet you got some good ones.
probably not.
Yeah, those look good. Yeah, all of these look good. Although y'all are kind of ignoring a whole group of integers that I saw some of y'all actually using, a few of you, on the integers. Negative numbers are integers, right? What you got? I'll put into negatives, yeah. Okay, so whole numbers. Yeah. Okay, so I'm gonna stop at that point. The whole numbers, you start with 0 and you need to go 1 and 2 and 3 and so on like that, right? That's the whole numbers, including the 0. And then integers, you got all the whole numbers, but you also have the negative integers and so on, okay? So all the whole numbers are in the integers. And so whenever you listed a whole number down here, that was true, but there are negatives that would go here that don't go up here, all right? Then once you get to rational numbers, it's all of both of these, but also everything in between as far as if it can be a fraction, okay? So basically you can think of fractions and decimals. Like I could put 7 up here, and then over here I could put 7.1, right? Or 7 over 1. So all the whole numbers and integers are rational, but then you can also divide A over B, any whole number over, or any integer over another integer. As long as you have an integer there and an integer there, you've got a rational number. So it can be whole numbers, but it can also be 1/2 and 3/4 and -8/7 and all that. Okay, irrational, you normally see a what with it? A lot of y'all had a square root, like square root of 2. Now, if you say square root of 49, like he had, well, that simplifies to 7, or square root of 4, or something like that. But if it doesn't simplify to a whole number, then it's going to be irrational. And how can you tell if you write it down without the radical that it's irrational? My square root of 4 is 1.41 da 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 da, right? It goes on forever and ever, never repeats. So that's by irrational. These rational numbers do eventually repeat, like 0.33333. It goes on forever, but it's repeating the 3. Or they'll just stop and just repeat 0 after that, I guess. Like 1/2 is 0.50000. Okay, so these can be decimals, but they either terminate or they repeat. Here, they don't terminate and they don't repeat. Okay, and you get the square root. Also, pi is an example. It's not a root, therefore it's called a transcendental number, but they're irrational also. And then the complex numbers are like we've been talking about with imaginary with an I in it. But complex really includes all of these because remember, complex has a real part, a plus bi, and that a part can be any of these. You can have a square root of 2 plus 3i or something. Okay, but normally when we have a complex number, we don't talk about it being positive or negative or odd or even or anything like that. What else? The main thing I want you to know is the difference between rational and irrational right now, because we're going to be looking at rational roots and irrational roots. And then we'll also be looking at complex roots, imaginary roots of our polynomial equations. And so when I say irrational root, I want you to be, automatically think of something like this, or a rational root would be something like that. Okay. Although a real root would be any of these, real. So we use the vocabulary in this next section quite a bit. And so I wanted to make sure, just give you a brush up on that. Now, Candace said she had a question on, see which one that was. Number 75. Where am I? 4. Let me look at that real quick. Use the quadratic formula. I don't think I did that one, did I? Because it looks a lot like 73. I don't remember which one I did. Okay, so that black marker is, let me try that blue one. I'm gonna go to my Amazon wish list that all the parents have access to and put dry erase markers just for me. Black ones. Although I love the colors, but the black is easier to see. 4x squared plus 16x plus 15 equals 0. So you're supposed to use the quadratic formula, which is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So here 4 is a, 16 is b, 15 is c. So x equals negative 16 plus or minus 16 squared minus 4 times 15 all over 2 times 4. Okay. Oh, now the calculator, which I probably took back to my desk. Good imaginaries there. You can put your whiteboard back up. Okay, so negative 16 plus or minus, so 16 squared. See, I don't even think, 256?
Should Instead of 226, 256.
I think you're right, because it's 2 to a power and 16 is a power. 256? 256, yeah. Minus, and that's going to be 16 times 15, which isn't as big, 240. So it's not even going to be an imaginary number. Because you know that you're going to have an imaginary root when this becomes a negative in here, right? That's the whole key. This is called the discriminant, because you can tell by looking at this number in the radical whether you're going to have an imaginary root or an irrational root or a rational root. So what's 256? It's probably 16, right? Minus 240 is 16. So it's going to be negative 16 plus or minus the square root of 16, which is 4 over 8. So let's reduce that. We can divide each of these by 4. So minus 1 divided by 2. So let's see what we get here. Negative 4 plus 1 is negative 3. Negative 4 minus 1 is negative 5. Do y'all remember doing this one and getting that by any chance? Yeah. Okay. Can you see all of this? I'm going to move the camera over a little. Just from me looking at it, it looks like it's at an angle. And then I can get out of the way. Yeah. That all shows good. Okay. Now we're going to look at section 2.5. Did anybody else have another problem to look at? Y'all got all those turned in? So James, just so you know, open containers are not allowed in classrooms because if you spill it, it makes a big mess. You have to have something with a lid. I'll let you have it today, but for now on, if you're going to have something to drink, make sure you have a lid that's fitted on it. Otherwise, it'll make a mess. Okay, look at 2.5. That's page 154. So we've been talking about polynomial functions and being able to graph them. And we already know a lot about, if we see a function, a polynomial function, we already know a lot about it, right? We can tell if it opens up or down, right? And what the end behavior is. So we've learned how to figure out the end behavior. And I kind of think of opening up or opening down as part of end behavior, right? End behavior. What else do we know? The degree, what does the degree tell you? I mean, that's the highest power. Tells you what? Huh? Turning points? Yes, because n minus 1 is number of turns and are the maximum number of turns. It won't have any more than that. And then n tells you the highest, even or odd. If they're all even, all the powers are all even, it'll be an even. And if they're all odd, it'll be odd. But even then you could have shifts, so they might be symmetrical. Yeah, but what?
I whispered the answer.
Oh.
Someone would get it.
The number of solutions.
The maximum zeros or solution. Okay, the maximum number of zeros or solutions. In fact, n, we're going to find out, will give the actual number of zeros if you include all the rationals and all the irrationals and all the complex roots. It'll be actually just equal to. Okay, we're going to talk more about that. So we're already finding out a lot about polynomial functions, and quadratics we can pretty well graph. If we didn't have a graphing calculator, you could probably figure out how to graph a quadratic pretty easily, because you know it's either going to open up or down, and you can figure out where the vertex is, and you can get another point maybe. And so you could probably sketch that out, but polynomial functions could be something like 149x to the 7th minus 2x to the 5th plus pi not pi. Okay, square root of 2x. You know, it can be really weird. Usually these are going to be integer, though, not something irrational or fractional for the most of the ones we're talking about. So we're going to learn some other techniques because other than quadratics and some cubics, it gets harder and harder to know how to graph them, to know enough about them to graph them. Okay, and so we're going to learn the tricks that they developed before graphing calculators came out and the way that graphing calculators actually are able to do this stuff for all the different kinds of polynomials we can have. And this is actually something that mathematicians back in the 1800s, they just spent hours on. They loved doing this, trying to figure out all these different rules. Like we're going to see one called Descartes, like Rene Descartes, his rule of sines. And like thinking, how did they come up with these? This is amazing. So first of all, they start off on page 154 talking about the fundamental theorem. And the fundamental theorem, you hear it in different forms. Here it says that if a polynomial has a degree n, where n is greater than 0, then the function has at least one 0 in the complex number system. Now, when we say complex number system, we're talking about reals and imaginaries. Okay, so in other words, it's gonna have a root somewhere. We may not see it on the x-axis, crossing the x-axis, but it'll be somewhere. And then it says, using the fundamental theorem of algebra and the equivalence of zeros and factors, you obtain the linear factorization theorem. Okay, and so in other words, you can take any polynomial and you can factor it down to linear binomials, or maybe some, no, they say linear factorizations, yeah, all linears. And once you know those linear factors, then you know the roots, right? Because if you have x minus 3, then you know that's going to cross the x-axis at 3. And if you know all these different numbers where it's crossing, that's going to tell you a lot about it. Especially if it has a multiplicity, an even multiplicity, you know, it's going to hit and bounce. If it's odd up here, then it's going to go through the x-axis. So we've learned a lot. And apparently, polynomials can be really hard to graph without a calculator. They can get complicated pretty easily. Okay. So let's go back to, there was something else I was going to mention about the fundamental theorem. I saw it on a video. It'll come back to me. They also mentioned that these two theorems here are existence theorems, which means it tells you that something exists, but it doesn't tell you how to find what it is. It just says there is such a number, but good luck finding it. Okay, there are a lot of existence theorems, and you think, well, what good is that? But it is pretty good, because if you're going to spend years of your life trying to solve something, you want to know that at least there's something that there is an answer. I mean, what if somebody else proved that there is no answer? Then you've wasted all that time. Okay, so the first example they have there, they have a polynomial function, pretty simple one, f of x equals x minus 2. Now you should be able, in your brain, picture what this looks like on a graph. Can you do it? Are you doing it? Where is it crossing the y-axis? Y-intercept, right? And it has a slope of 1, 1, slope of 1, right? And so you should just automatically, when you see that, you think, okay, it's going through there, and it has there it is, right? Y'all pictured that? It's supposed to be around a 45 degree, I don't know. Okay, and it's a first degree, right? Because it's x to the 1. So how many times does it cross the x-axis? 1, right? And it has exactly 1 0. And every linear function is going to do that. Can you, well, unless it's horizontal. But if it's not horizontal, it will go through. And if it's vertical, it's not a function. So we don't even talk to it. And then it says we have another one, x squared minus 6x plus 6 plus 9. When you factor that, you get x minus 3 times x minus 3. So does it go through 3 twice? 3 is a root, right? But it doesn't go through 3 twice. That would be kind of hard because then it would have to be like kind of come back around to it or something. Can't do that. So what that means is this is basically squared, right? It's got a multiplicity of 2, which means it is going to cross 2, or not cross it, but it's actually going to come down and touch it and then bounce back off somehow. Okay. And so it's called a repeated 0 because the factor is repeated, but you don't see it going through it more than once. Repeated 0 or multiple. And then they mentioned, okay, on this right here, this was the multiplicity. So it has 2 roots, but they're both this. It's a repeated root. So, but it still has 2 because you had this twice. So they consider that 2 factors, 2 roots, even though it's the same number. That's kind of cheating. And then look at the 3rd degree polynomial function, has 3 zeros. Let me erase and write this one down. We get out at noon, right? Yeah. The dots, I get it all. Okay. We have x cubed plus 4x. Okay, so it's a 3rd degree, so it should have 3 roots. But when you factor that, well, first of all, you can pick an x out, and that'll be x squared plus 4, right? And then if we try to solve this for 0, like x can be 0, or x squared plus 4 can be 0. It's not a difference of squares, so we can't factor it as a difference of squares. It is a sum of squares, x squared plus 2 squared. But we'll do it this way. We'll subtract 4 from both sides, and then we'll take the square root of -4. And you're supposed to do the plus or minus square root of -4, which is plus or minus 4i. 2i, sorry. Square root of 4 is 2. So you get an I. Okay, and so it has 3 roots. It's got 0, a real root that you'll see it go through the origin, but then it also has 2 unreal roots or imaginary roots. Positive and negative 2i. Okay, so y'all want to go to a whiteboard or just get your little one out for a short problem? Little one, get your little one out. You need the checkpoint. It's going to put a test to your factoring abilities. Write down f of x equals x to the 4th minus 1. Determine the number of zeros. Well, that part's easy, actually. How many zeros maximum will it have? 4. Okay, find them. Find them. Anybody getting them? Can this factor in any way? Think of it this way. X squared squared minus 1 squared. The same thing, right? And remember, a squared minus b squared is the same thing as a plus b, a minus b. In this case, a is x squared, b is 1. Everybody get that far at least? Are we done? Nope. Now x squared plus 1, you can't factor that any further, but now we've got another difference of squares. X squared minus 1 is another difference of squares. Right. Remember, we had to come up with 4 roots. Well, I've got these 3 factors. So let's just set them each equal to 0. So I'm leaving the last step to you. I'm going to come around and see what you got. They got 4 roots yet? Yeah.
Okay.
And yeah, good job. So that's 2, right? Plus and minus, yeah. 0. No, not actually. 0 is not going to work. Plus or minus 1. Because you're subtracting this from both sides. That should be -1, which means when you take the square root, what do you get? You can just scribble something and say that's the answer because I can't read it.
Oh, that's not that.
Oh, okay.
That's not that.
You're almost there. Nope. That's that and that is the same thing actually.
Yeah.
You see?
Mm.
What would you get from this one?
1.
Right.
-1.
You got negative.
Yeah, but then
Oh, I see what you're saying. That's okay. That's a negative. I'm sorry. I thought it was x. So this is from this,
Yeah.
and then you'll get 2 more from that. Yeah. Okay, I see. Yeah. Good. When you take the square root, you take the positive and negative square root. Okay, so as most of you, I think I checked nearly everybody. So here you're going to get x equals plus or minus. Some of you said square root of -1. Same thing as plus or minus I, which is plus I and negative I. And then here you get a -1 and then a 1. So those are all the roots for that one. Okay. Set your board aside, but you'll probably get to use it again. Now we have what's called a rational zero test. Okay, so like here, both of these were rational, but this wasn't rational. It wasn't even real, right? So we're looking, they got a way to test to see what are the possible rational zeros that we could have. It doesn't deal with any of the imaginary or irrational roots. And here's the deal. Let's say you have, I don't like the way they listed in the box on page 156. That's really annoying how they did that. Because 55, you're right, I'm sorry, 155. They use this P and over this Q thing, and then they have this. So let's say you have f of x equals 9x to the 5th plus all this stuff, and then maybe plus 2x squared minus 3x plus 1. Okay. And so you've got a lot of terms here. The thing you do for this rational zero test is you look at the leading coefficient and the constant coefficient, this constant they have way at the end, okay? And what you do is you put, this is considered to be P, and this is considered to be Q, which really bothers me because that's putting Q before P, but alphabetically P comes first. So I have to remember it every time. But anyway, if you take a fraction P over Q, and they have no common factors other than 1, then the possible rational, because rational, remember, is an A over B kind of thing. Zeros are, how do they put it? They just say equals factors of P over factors of Q. Okay. So what are the factors of 9? Let me do this. So 9 has factors of 1 and 3 and 9, right? The only factors it has, yeah. And what about 1? 1. Okay. And if you think about it, plus or minus on both of them. You can even do plus or minus on that, because -1 times -1 will give you 1. Okay. So if we set up 1 is P, so we're gonna put that on top. 1 over 1 is a possible factor, and 1 over -1 is a possible factor, and -1 over 1, but that's the same thing, right, as 1 over -1. So I could just say 1 or -1 if I mix these up. And what about if I do this? That'd be basically plus or minus 1/3, right? If I put 1 over 3, depending on the combination of plus and minus. And then I could have plus or minus 1 over 9. So that's 1, 2, 3, 4, 5, 6 possibilities that this could have one of those rational, or more than one of those rational roots. In other words, if it's going to have rational roots, it'll be in this group. Okay, none of them, it may be all imaginary roots or more all irrational, but if it's going to have rational, it'll be these. So then you got to start trying those out. So it narrows it down. That's the rational root test. It just narrows down your choice, because it's basically you have to just trial and error. And if you're going to trial and error, you don't want to have to trial and error an infinity of things. The choices. So this breaks, it now only have 6 choices. And then what you can do with that is do synthetic division, right? Because if you do synthetic division of this with the 1/3, you know, see if you come out to 0 at the as a remainder. So if you come out to 0, then it's a root. If it doesn't, it's not a root. Try another one. And normally we'd probably start with 1 and -1, right? Those are a little easier. Okay, so get your marker board out and write down f of x. This is so easy. X cubed plus x plus 1. Okay, so what are the possible rational zeros? I want to say roots. Zeros. Okay, so write down what you think the possible rational zeros are. Because you have basically your your Q is 1, and your P is 1. And so what are the factors of 1 and 1? And if you made a fraction out of that, you're basically gonna get what? 2 numbers, plus 1 or minus 1, right? Okay. And that's it, because there's no other numbers to try. Okay, so if we're gonna, so it's kind of nice knowing that I only have to try these 2 to see if they're gonna work. So let's try those. Okay, so what would you do? You'd set up your, you wanna do +1 or -1 first? We'll do +1. Okay, so we put a 1, and then there's a 0 squared term, and then a 1, and then a 1, right? Cube squared, okay. Uh-oh, didn't get a 0, did I? That means though that the point 1, 3 is on the graph. I mean, that's kind of nice. Remember, because of remainder theorem. but it's not a root. So let's try -1. Okay, so that bring down that's -1, -1, that's +1, which gives you 2, and then that gives you -2, and that gives you -1. That doesn't work either. Dang it. Okay, so we've tried all of our possibilities. So we can say for certain, because of this test, there are no rational zeros. And that's a good thing to know, right? Now we know it's cubed, and so how does that, and then it's positive. So what's the end behavior for that? Remember, it's a positive odd function. So do the arm stuff for that. Kind of a this thing, right? But 0 is not a root and 1 is not a root, but it's going to have a root because it starts down here and it ends up there. So it's going to have a root somewhere, but it doesn't have a rational root, so it must have a irrational root. Okay, and they show in the margin there on page 155 that it does, and it is, well, they don't tell us what it is, but it's between 0 and -1, but it's irrational. Well, how could you find that? Because you can't use a quadratic formula. You'd have to be able to factor cubic functions, and that's pretty tricky.
There is a formula for it.
There is a formula that has square roots of square roots. Remember we saw in that video? So there is a formula for it. We're not gonna, they don't put it in any high school book that I've seen. Of course, we have calculator. We can just type it in, and there it is, right? That's kind of nice. Now look on page 156. We got a couple of minutes here. I want to come back further this way. Actually, I'm going to come over here. It's a little easier in this to see. Let's look what they do with leading coefficient of 1. So our simplest thing is when our leading and ending coefficient were both 1s, right? But we're not always that lucky. But sometimes we have just the leading one is, so we got x to the 4th minus x to the cube plus x squared minus 3x minus 6. Okay, and so here's the one that's, always have to look, Q, right? And this is P. And so I'm just going to put -6, this is P over Q, right? Yeah. Over 1, but all the factors of -6, which are what? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So that can be the numerators. And then the denominators would all have to be plus or minus 1, which basically it means you're just gonna, you could just erase that and say it's one of these 8 choices, right? That's the nice thing when the coefficient, the first one is a 1, it has a 1 down here, and then you have whole numbers to try. Okay. Gosh, they let them out early. And so then you could start doing your synthetic division, you know, pick them out and see which ones. That's only 8 to try, and synthetic division is pretty fast. So you could do that, right? But they do, they tried -1 and it worked, and they tried 2 and it worked. Lucky guesses. And then they got it down. Once they did, see it's x to the 4th, once they divided it by 2, like the -1 and the 2, after you've done that synthetic division a couple of times, you're down to a quadratic, right? And once you get down to a quadratic, then you can just factor it into parentheses. You don't have to do synthetic anymore. Okay, so they got a drawing, the sketch of it's there in the middle of the page. Doesn't that look weird? Kind of like a finger pointing down. I don't know, it's odd. And you can see where it's got, it looks like a 1 and a, but it doesn't say what they actually all end up as. A 1, a -1, a 2. Okay, and then some unreal ones apparently. that x squared plus 3 is going to give you imaginary roots. So it's going to have 2 imaginary roots. So it ends up with, it's a fourth. It's got 2 real and 2 imaginary to make 4. Okay, so we'll come back there tomorrow. And we'll probably have to do half of this section now and the other half after Thanksgiving. That's going to be interesting. So no assignment. That's nice too. No more pre-cal assignments till after Thanksgiving. We've only got 2 classes to go. But still, it's a good break. All righty, Candace, I'll talk to you later.